Okay, so this is all very nice, but we still have a potentially large training set and a certainly vast number of constraints that result from all these possible but wrong labelings that we need to consider. And rather than solve this problem exactly, we're going to use cutting planes as an approximation. So in cutting planes, we proceed as follows. We solve the unconstrained problem. We then find the most violated constraint and add it to the active set. We then solve the constraint problem and iterate. Now, as an algorithm, this is what it looks like. Some people are faster than others here. Maybe you should pick a different seat. Okay. So here's the algorithm. As input, we have training data xi, so our structured input and the true structured output that goes with it, and a tolerated error epsilon, and our output is going to be the new parameter vector w. Now we start by defining the constraint set K to be the empty set, and also set our normal vector and the slack variables to 0. I have a comment on the constraint set being 0 initially. Because these were the constraints that we used. And I can leave out the non-negativity constraint on xi if I use a slightly different set here. So I could also write that W transpose delta psi I of y should be greater than or equal to the loss minus xi I. Now note that I'm omitting the second constraint, the positivity of xi, and I'm now saying that this should hold for all I and for all possible outputs, including the true one. Because if you now insert the true output in this equation, you will find that 0 is larger than or equal to 0 minus xi I, And I have to ponder this. Yeah, and from this, the second equation follows by itself, because we say that 0 is larger than or equal to 0 minus psi I, and then psi I has to be non-negative for this to be true. Okay, so these two sets of constraints have now been collected in a single one, and the difference is that here the true labeling had been excluded, and now it's no longer excluded. So this gives an even more compact formulation. And this is why we start with an active constraint set now, and then repeat the following. We remember the old constraint set. And then have a loop over all training examples and ask for the most wrong prediction. So we are looking for the prediction which has the biggest loss and at the same time the smallest margin. So this is a solution which, given the current direction of W, is very close to the true solution, and yet according to our loss function is very wrong. So this is why I want to call this the most wrong prediction, or perhaps the most misleading prediction, the most vicious prediction. And if this prediction is sufficiently vicious, we want to include that sample in our active set. So if the difference of the scores so if the difference between the scores, if the margin is less than the loss function and the slack that I find and this tolerance epsilon, then I'm including this constraint modulo this bit of error which I tolerate, then I'm including this constraint in the active set. and am resolving for the new parameters. By minimizing over our regularized loss. Subject to all these constraints. And in the last hour we've seen how to solve this in the dual. But you could do it in the primal if you want. Sorry, the end is for the 4. Should sit here. And this is repeated until the constraint set no longer changes. So the expensive parts are here and there. This is expensive, and that is expensive. And here in particular, I mentioned the loss function that should be decomposable. Here you see why, because in this maximization, we are not only looking at the point that, as judged by our parameter vector W, lies furthest in the direction of the true output, but we want at the same time to evaluate the loss. And again, this set of possible outputs is vast. This is a huge set. And this is why we want a loss function that should be as tractable as the rest of the expression. So this equation here, that's the reason why the loss function should decompose over the problem. For example, if we have a Markov random field, then this would be the map solution. And here we're looking for the map or maximum or posteriori solution, not of the original Markov random field, but of the Markov random field augmented with an additional loss function, with an additional term that hopefully decomposes just as the rest does. Now there's always an easy way out. The easy way out for the loss function is to simply use the Hamming loss. So if you use the Hamming loss, you simply count locally the number of disagreements between your true output and the predicted output. But preferably you would want loss functions that capture more of the structure of your problem. And finding such tractable and yet non-local loss functions is a topic of current research. Okay, so I want to give a few examples. Yes?
The if statement. I'm confused by the why, because why is all possible
Oh, it should be y hat. Sorry. Excuse me.
So this means we don't choose the maximum violated, but any that's violated more strongly than we allow, right? Because we don't get all the constraints first, and we don't avoid all the constraints first, but as soon as we see one's more violated more strongly, then we allow it because
I didn't get the difference. Can you say again, please?
We go through the loop, and as soon as we find a constraint that's violated, we then minimize it. So we don't specifically look for the one that's the most violated.
It is in this line that we are looking, that we find the most bad solution, because if we had just the second part, we would find, so we want to So if we looked just at the second part, here we are maximizing the negative margin, which is the same as minimizing the margin. So we would look for the wrong solution that still gets the highest score, if we just look at the second part. And here with this first term, we take in addition into account how bad this wrong solution is. So let's say we have the score here, and the true solution, or the score of the true solution, would be W transpose psi of xi comma yi. And now we have two wrong solutions. Let me say this is W transpose psi of xi comma y tilde, and another wrong one, W transpose psi of xi comma y wiggle. And if we looked only at the second term, then we would say, and then we would have many other wrong solutions. And here we've picked out, a zillion. And here we've picked out only the highest ranking of those. So if we looked only at the second term, we would pick this one here as the most violated. But now in addition, we're looking at the loss function and asking, according to the loss function, how bad are they really? And then it could be that this one here, even though it has a lower score, we absolutely want to avoid it because it's very, very wrong according to our loss function. And this is why we add these two terms up. And then it could be that the one down here, or even one further down, is the most violated constraint, which is then added to the constraint set. And you're right, I forgot the hats. Make sense? Okay. For the K, I don't need to what? Yes, this is, you're right again. It means I want to include this sample. No. I think I need the hat. Okay, let me look it up in the paper after the break, okay? I think it's right like this. Let me see if I find it immediately. Yeah, the hat needs to be there. Okay. Good. I want to finish by giving a few concrete examples in the hope of making this more concrete. For example, this lazy hiker, this was the running example that I used, where X would be the height map of a terrain, and Y would be the path that people take. The goal is to learn a utility function that trades off, that finds the right trade-off between distance and steepness, just like humans do. And I could, for example, use the following psi of x comma y. I could take a vector which sums up, for instance, the detours. By detours, I mean the following. I'm taking a model here where the hiker always has to start at the top left corner and always has to end at the bottom right corner. And I only allow monotonous paths because then I can solve it via dynamic programming, otherwise I can't. And the shortest path will be to just make a diagonal move. And whenever I make a non-diagonal move, such as a horizontal one, it means that my path is going to be longer than totally necessary. This is what I mean by taking the sum of detours. I'm assuming here that a straight diagonal path will go from beginning to end, from start to end. So I could take the sum of the detours. I could take the sum of the absolute values of the steepnesses integrated along the path. But nobody tells me that my decision boundary is going to be linear in the sum of the detours and the sum of the absolute values of the steepness. Hence, I'm also including here, because I don't want to invent a kernel, hence I'm also including here, for example, the detour squared and the squared values of the steepness. And you can take any other features that you imagine to be useful. Now the loss function I want this loss function to somehow measure the difference. Let's say I want to measure the difference between a correct path and between a wrong path. And it would be nice if I could still use dynamic programming to evaluate the sum of this loss function and the difference of the scores at the same time. And something that I could do, for example, would be to measure something like the integrated distance of the second path from the first. So here the ground truth path is given. So I could, for example, do the following. I could compute ISO distance contours. This would be distance 1, distance 2, distance 3 from the true path. And I could now say that my second path integrates over these distances from the first. So I could, for example, obtain, so these green lines here, I could obtain them from a Euclidean distance transform of the true path. For example, you could invent other things. I'm just giving an example. And now to evaluate this loss function, I would trace out the second path and integrate this the Euclidean distance transform generated from the first path along the second path that I've actually taken. This would be one example that would still be amenable to dynamic programming. And that is also the reason why I restricted myself to just monotonous paths, because then I can use the simple dynamic programming approach to find a path that, on the one hand, given the current parameterization for my vector W, will minimize the sum of the detours and the steepness with these weight functions that I will find, and at the same time will try and stay close to the true path. Now, wrong. For the most violated constraint, I want to find a path that is as dissimilar as possible from the true path, and which yet has scores well. Okay, so that was the lazy hiker as an example. I have many more. I want to show at least one. This is work from Xinghua Lou, who used to be in this group. He's now a postdoc in New York. And the notation here is slightly different, but the problem I think is interesting. So he is looking at cell tracking, and he wants to learn the parameters of the tracking algorithm. In his framework, cells are allowed to divide. So here we have time t plus 1. Cells are allowed to divide, so you will see that this is only, or can only be formulated as an integer linear program, like we discussed in the last hour. Now, you can compute many features for your integer linear program. You could, for example, ask yourself, if I want to, in this tracking by assignment, if I want to evaluate the probability, or if I want to get a score for associating this cell with that one, this score should probably depend on the distance. So how much would the cell have migrated? So for example, if this is the frame of reference, then this candidate here is pretty close to that one. So distance-wise, it will score well. For example, associating this cell with that one here would not be so good because it's much further away. But it would also not be so good because this is much bigger than that one. And I'm assuming that the size of cells does not change vastly between two frames. So we can take into account distance, we can take into account size differences or intensity differences, or more generally appearance differences, and if you think a little, you can easily derive 30 or 40 features, not knowing in advance which will be relevant for the tracking and which not, or in particular you won't know what the weights for all these features should be. So, you know, if you look at distance versus difference in size, how would you weight these two in your tracking? And what Tsinghua did was to learn all these parameters. And that is now an example of a structured learning problem, because I still want to get out valid tracks in the end. And the score is here written as L. It depends on, I think L was chosen for likelihood, even though it's not a probabilistic method. It depends on the input X, so the images, or your cell candidates that were detected. Then it depends on assignment variables Z, those are the labels. So if I associate this cell with this one, then this is one possible event, and in this case it has an indicator variable Z set to 1. If I associate this cell with that cell, that's a different event, and in the particular, well, because I'm not drawing an arrow here, it means that in this particular event I set this indicator variable to 0. By the way, also this is in the table here. So there are all these events that you can hypothesize. So how the cells in the first image, or how a candidate in the first image relates to the candidates in the second image. And for each of these hypotheses, I can compute features, and I can set this indicator variable to 0 or 1. And now this is at the heart of what the structured problem is, namely, I cannot simply say, yeah, this assignment looks very good, so I'm switching this indicator variable on. And I also like that assignment very much, so I'm also switching that indicator variable on, because you know that each cell can have only a single fate. So you have a constraint here that the sum of all the indicator variables, or all the things that the cell can do in the future, there can be just a single explanation, so those indicator variables must sum to 1. And each cell only also has a unique history. So all the indicator variables that are associated with a given target cell, they also have to sum to 1. And then we don't want fractional explanations, like saying maybe the cell went here, but maybe it went there. We want these indicator variables to be strictly binary. Okay, so here is your score function. And here is how you optimize, so how you solve for new parameters W. Namely, you minimize the sum of the slack variables, like you've seen, plus a regularization term. And the regularization term, we have always used this L2 term, which leads to a nice quadratic program in the dual. But you could also use an L1 term here. So you could put a penalty on the sum of the absolute values of your individual coefficients. And that has the effect of giving you sparser coefficients. So you will find more of these parameters to be 0 in the end. And that is beneficial because perhaps out of the 40 features which you have computed, you only actually need 20, let's say, for good quality tracking, and that will save you, of course, lots of computational time. And then, well, down there is a table that gives results. And the bottom line is that when you learn few parameters rather than hand tweaking them, you can improve performance. And however, if you hand tweak or if you do a grid search, you can only optimize over 4 or 5 parameters because, you know, try yourself. Adjusting 40 parameters, you just cannot do it by hand. And even grid search, you know, beyond 5 or maybe 10 dimensions, it becomes hopeless. So when you have something like 40 dimensions, you need something like a learning strategy shown here. And in this example, it also turns out that you can obtain better trackings or lower error rates if you admit a large number of features. You get a more expressive model than if you only use the 4 or 5 features which you can still parameterize by hand. yeah, so there's an example of how you can use that in tracking. This is starting to find more applications now. So if you look in the current literature, you find, well, people who try to use that for image segmentation and so on. As you've seen, the structured learning is not a plug-and-play method. So in particular, the choice of this feature space, so where you map both your input and your structured input and your structured output to a space of given dimensionality, this is all but automatic. You, the expert, the designer, have to do it. And secondly, there's this question of loss function. You would like something that's not totally local. You would like to have some non-locality in there, and yet keep it tractable at the same time. And then you need a good inference algorithm to find the most validated constraint. And this best inference algorithm will be closely coupled to the way you formulate your problem and your loss function. So it takes a lot of expertise to set up these models. Okay, so it's the end of today and the end of the term. We've covered huge amounts of material, and we've sat here together for something like 50 hours. It's a long